Yes, so I told that there are the experimental methods for polymer determination of molecular weights is based on or is conducted with polymer solutions. So let us now see those that mechanism of solubility or the phases of solubility before we start an experimental method. Now, a polymer is basically when it is in solid form, you have to put it in a solvent, suitable solvent, and in fact, put a lot of effort to make it solubilized. Usually, the polymer solutes don't dissolve readily in solvents. But however, whatever the case, you can still solubilize it. At least when the solutions are dilute, the solubilization is easy. Now, there are certain characteristic stages in which the polymer solutions dissolves. In contrast to a low molecular weight solute, a low molecular weight solute instantly dissolves. See, what are the two important steps in dissolution? First is the solvation of the solute molecules. So if, for example, a glucose is put in water, what happens? The glucose molecules are solvated, and then the diffusion happens. So, and then of course, because of this diffusion, there is a homogeneity in the solution later. It can be very instantaneous. If a solute is, all these three steps can happen instantaneously if the solute is soluble in solute. But for a polymer solution, it doesn't happen instantaneously. Therefore, there are some extra terms which have to be coined for solubilization of polymers. Now, if you look at the polymer compost, which is in the solid state before being added to the solvent, now you see the chains of polymers always. And of course, the chains can come in various shapes. I have just shown you almost a random coil like this. It can be too much coiled. All those shapes are still possible. But whatever the case, the chains are held tightly because of strong intermolecular attractions between the chains in the solid phase. Now you put that in the solution. What happens now is that the solvation process is slow. The solvent molecules are, if you compare the sizes of the solvent molecules are too small compared to the gigantic size of the polymer chains. So what happens? The solvent molecule, of course, see, what do you mean by solvation? It is a process of breaking the force of attraction within the solute molecules and establishing new force of attraction between solute and solvent molecules. And this process is slow. That's what I was talking about. Why? Because of the size difference, basically. And then there is a lot of thermodynamics involved in this, the solvation of polymers, and I will not touch upon that. I'll just briefly mention a few things. The solvent molecules, initially what they do, they surround the polymers chains, of course, no doubt. Then as the solvation is happening, sort of a competition is developed between two things. One, the aggregation of the chains, and the other process, the solvation. So the aggregation of the chains tend to hold the chains together, whereas solvation tends to break the chains. How does the breaking happen? Because of overcoming the intermolecular force of attraction between the chains. So in fact, if you after some time of addition of polymers, there is an equilibrium reached. In that equilibrium state, you can see that the chains are partly broken and partly solvated. So they are partly aggregated and partly solvated. Why? Also inside the polymer matrix, the solvent molecules diffuse. It's also important. This, because of the huge size, it's almost like a three-dimensional network inside. So the solvent molecules also diffuse inside the polymer solution, polymer matrix, and you can now recognize two types of solvent molecules. The bound solvent molecules inside the polymer matrix and free solvent molecules at the surface of the polymer matrix and after that, beyond that surface. In fact, there is again an equilibrium between the bound solvent molecules and the free solvent molecules. So these two equilibria exist simultaneously. And the combined effect of these two equilibria is that, first, there are two effects of this equilibria. First, the lumps of polymers, the solid what you have added, is slowly solvated and solvent molecules are taken inside. Because of that, swelling happens. So the chains you can see here, these chains from the inside, they are solvated. Outside also they are surrounded by the solvent molecules. Therefore, before the diffusion takes place, swelling of the chains happen. And now the whole sphere, the swollen sphere, starts to diffuse, starts to move. Anyway, the movement has to happen, right? Because of translational energies will start to move. Now, this sphere in which the solvated polymer molecules are there. And of course, these spheres are found fully dispersed in the solution. So what is the difference now? The solution does not contain individual molecules of the solute. Instead, it contains swollen aggregates of the solute. And this is referred to as hydrodynamic volume. Now, hydrodynamic volume term is important to us because this is a function, the viscosity is a function of hydrodynamic volume. Okay, we'll come to this point later. Now you can see that the solubility of the polymer itself depends on a lot of factors. Crystallinity of the polymer, whether it is in amorphous, crystalline state, all those things. And very important is this molecular weight. The same polymer with different molecular weights has different solubilities and branching polarity. All these, of course, affects. Cross linkages are also again very important, particularly for the hydrodynamic volume. Branching and cross linkages are very important. Okay, fine. Now, okay, fine. You can classify the solvents as good and poor solvents. So which is a good solvent? A good solvent is the one which solubilizes the polymer with an ease, readily. So at a molecular level, a good solvent has higher attraction towards the polymer chains, polymer molecules than itself. Fine. Whereas a poor solvent, it has higher attraction for its own molecules than that of the polymer molecules. This is the thing we can use everywhere in any solutions. Poor solvents. Why do all solvents don't solubilize all solutes? Why? Because of all these factors. Now you can somehow prepare a solution by carefully manipulating so many factors, in which the polymer solvent and polymer interactions are of the same magnitude, and this state is called as theta state. Okay, so what is a theta state? It is a situation in which the polymer solvent and polymer interactions are same to the same extent. Now in that state, whatever the solvent you have used is called a theta solvent. theta solvent. And for a theta solvent, how to quantify this theta solvent? I mean, we are just simply telling, right? The interaction is different, the interaction is same, all these. But how to quantify that? Anyways, you look at the hydrodynamic volume of three cases. When a polymer is in a very good solvent, it is more, the hydrodynamic volume is more compared to a theta solvent and a poor solvent. Now, theta solvent is almost like between a good and poor solvent. So this theta factor is expressed in terms of a constant called alpha, which is called linear Emmett factor. For theta solvents, the alpha value is 1. Now, the distinction starts now. How to choose solvents for your polymers? See, when you are working with polymers, there are many solutions you have to make. And when you're repeatedly working with them, you have to even change the solvents. So how to choose which solvent is good for my polymer to make a solution? For that, you can always refer to this chart. I mean, because of all previous literature, in literature, you get this chart. And of course, this hydrodynamic volume is temperature dependent also. Very important factor. So you can have a theta solvent if the alpha is 1. If the alpha is greater than this 1, they are all very good solvents. They are good solvents for your polymer. If the alpha is lesser than 1, they are poor solvents. That is the bit practical significance of this theta solvents. So ideally, in fact, why this theta solvent discussion is also important, because in some experiments, we are going to use this theta solvent concepts later. Okay, fine. Now we will move on to the okay, yes. So now we will move on to the viscometry. How the measurement of viscosity can be used to determine the molecular weight of the polymer samples. Now, you know, the viscosity itself is a characteristic property of fluids. Even pure solvents also have viscosity, not just the solutions. Like I said, when they are low molecular weight compounds you have dissolved in the solvents, they do not affect viscosity too much, but the polymers do. Now, why the polymers affect the viscosity so much? After all, what is viscosity? It is the resistance offered to the flow of the liquid. And if you look at the models which explain viscosity, you can find that the fluid which is flowing can be visualized as layers of molecules. Now, when these layers of molecules are finding more friction, where does this friction start? If the layers of the molecules, there is a lot of intermolecular force of attraction, so the friction is more, and viscosity is more. Now you can break it also by applying temperature. You can reduce the viscosity. But anyways, so viscosity is okay. Now coming back to this polymer solutions. So what happens in polymer solutions? Why I told that viscosity simply increases with the concentration of the polymer solute, just because I told about this swelling, right? So these are the particles, swollen particles, which are fully dispersed in the solution. So naturally, these swollen particles, because of their unique size and the diffusion properties, alter the viscosity. Now the alteration is, like, fortunately, at least for to use it experimentally, is having a linear dependence. If you increase the concentration of the polymer, the viscosity of the solution also increases. Anyways, so now let us use some equations, and these equations of course are not meant for the polymer solutions alone. These equations are meant to find the viscosity of the given solvent or the given solution, any solvent and any solution. And the famous law which the viscosity by which deduces the viscosity using experimentally determinable factors is this. The viscosity Hagen-Poiseuille law. The viscosity is equal to pi R4 delta H P GT 8 LV. Anyways, it's you need not understand all terms in detail. It's fine because it's a law which it is existing since a long time, used extensively to calculate viscosity, where R is basically the flow rate and delta P is the pressure drop across the tube of length R and radius R. Okay, fine. Now, what are the factors which affect viscosity? These are the factors. Polymer and solvent type. This combination is of course important. Molecular weight of polymer, concentration of polymer, temperature. We are not it's not that we should find the absolute viscosity of the given solutions. Not required always. And even finding out absolute viscosity is difficult. So we work with a term called relative viscosity. Okay. And relative viscosity is nothing but the viscosity of the solution divided by viscosity of the pure solvent. In low molecular weight compound, the relative viscosity is always 1, or at least nearly equal to 1, almost equal to 1, because the viscosity has no effect. The concentration of the solute has no effect on viscosity. Solution viscosity and solvent viscosity are almost same, identical. But in polymer solutions, it's not like that. This ratio is important, relative viscosity. And if you use the previous equations, you can divide them under two conditions, that one for the solution and one for the solvent. So the like terms cancel and you are left with simply T divided by T naught. So what is this T? Time of flow. I hope, of course, in practicals this semester you should have conducted this experiment in your lab, finding out the molecular weight of the compound polymers by using viscometry. But at least it's okay. I hope that you remember how your Ostwald's viscometer looked like in your BSCs you have used. So basically viscosity there is calculated by measuring the time of flow between two marks in your instrument, right? So you are going to suck the liquid and start the watch clock, stop clock when the liquid starts flowing from upper mark, and end and record the time for the flow. So that's what. The relative viscosity is now a bit easier to calculate. Why? Because it's only a ratio. You need not know all these radius of the capillary tubes, length of the capillary tubes, because they are same for both solvent and solution samples. You are using the same instrument. So simply T by T naught now becomes an experimentally important data, T by T naught. Anyways, like I told you, absolute viscosity, it's difficult to obtain. Therefore, we use different terms of viscosities. One is the relative viscosity we have used already. This is the solution viscosity, solvent viscosity, and there is also called specific viscosity. And specific viscosity is you have to take the difference in the viscosity of solution and solvent, n minus n naught divided by n naught. So you can even simplify this as relative viscosity minus 1. So that is the specific viscosity. And there is also something called reduced viscosity, where see in all these viscosity terms the concentration is still a factor. For the same solvent solution combination, different concentrations of the solute give you different viscosities always, but you can make it independent of concentration by dividing by concentration term. So if you divide the specific viscosity by concentration, you are going to get a term called reduced viscosity. Now the last one is important for our discussions. Why? For our experiments. Why? And what is it? That is intrinsic viscosity. And intrinsic viscosity is defined as limit concentration tends to 0 specific viscosity divided by C. And please note that all these units, relative viscosity, specific viscosity don't have units, whereas reduced viscosity and intrinsic viscosity have units which are reciprocal of the densities. What is density? Grams per cm cube. This is reciprocal of this, cm cube per gram. Anyways, that was only some interesting thing I told. It's fine. Now, you think about this intrinsic viscosity term. Yeah, what is it there in its definition itself, where limit C tends to 0 means what? C means what? It's the concentration of the polymer or the solute. It is tending to 0 means your intrinsic viscosity is will have usually the values close to your solvent, pure solvent viscosity. Because if the concentration is tending to 0, you are approaching pure solvents without any solutes in it. Now, therefore, intrinsic viscosity is a term used in very dilute solutions, very diluted ones. Only a dilute solutions can give you limit C tends to 0, right? And for determining molecular weights, we use dilute solutions of polymers only, because the concentrated solution is very difficult to make. They have very large viscosity values, and these large viscosity values will not give you accurate results finally when you plot it on a graph and determine the molecular weight. Anyways, so in very dilute solutions like what we use in the determination of viscosities, intrinsic viscosity is an important factor. Now, how to relate the viscosities to the molecular weight? This is important, right? So all this time, what were we discussing? We were discussing the basic information about viscosities and the behavior of polymer when it is added into a solvent. Okay, I'm just running out of time. 10 minutes more, no problem. So what I will do is, don't send your names now, because next class, after I extend this class later, I will take the attendance once for all. Anyways, so when the time ends, I'm going to end the meeting. I will reschedule it. So immediately I will reschedule. Please relog in, all of you. Yes. So now, what I will learn till now, that the viscosity of the solution, polymer solution, is dependent on concentration of the polymer solution. Fine. But this concentration factor doesn't give you molecular weight, is it not? Because you can make different concentrations of polymer solutions by simply taking different weights and dissolving in the given volume of the solvent. So we require an equation which relates the intrinsic viscosity to the molecular weight of the polymer solutions, now of the polymer sample, and that equation is there. It was devised, formulated in 1950, first by Schrodinger, and then later revised, and now it is known as Mark-Houwink-Sakurada equation, or simply sometimes Mark-Houwink equation. What does it do? It relates the intrinsic viscosity with the molecular weight of the polymers. And you know, like I previously, in our previous lecture, we defined a term called viscosity average molecular weight. So what was it? Viscosity average molecular weight. It was the molecular weight, average molecular weight determined by from viscosity experiments, viscometry. Say, so simply putting molecular weight, average molecular weight here, we will specify it a bit and write viscosity average molecular weight. Okay. I mean, the molecular weights determined from different types of experiments will have different values. So, I mean, even I showed you a relationship between different molecular weights, number average, Z, weight average, Z average, and viscosity average. It was varying, right? Okay, fine. So now the Mark-Houwink-Sakurada equation relates intrinsic viscosity to the molecular weight of the sample, where K and A are the constants which are characteristic of the given polymer solvent combination and many other factors like temperature, all these things. Now, so the equation appears simple. If you know the intrinsic viscosity of the sample and K and A, you can directly calculate what is the molecular weight of our compound, of our polymer sample. But that is not as easy or as straightforward as the equation is appearing. So you have to do a lot of extra calculations. Anyways, what are those? First of all, determination of this intrinsic viscosity itself, because the viscosity value what you get from your experiment using Ostwald's viscometer has to be converted into intrinsic viscosity, because this intrinsic viscosity, your formula for calculations of yes, this is the formula for calculations. Anyways, let us consider this formula. This is the viscosity of the solution. It is not intrinsic viscosity, it is the viscosity of the solution. So now after determining viscosities, you have to convert that intrinsic viscosity using series of conversion formulae and then find it out. So that's the first thing. The second thing is how to determine this K and A without knowing this. Now, anyways, I'll just end the meeting now. I'll reschedule it. Please log in.